No, I'm not. Sorry, guys, 1 second. All right, guys. So welcome back. I know we're all anxious to get our exam results back. Because I've been traveling, I have not had time to finish marking those, but I will get them done as soon as possible, no later than the start of class on Wednesday. I'm hoping that you guys looked at the material I posted for you over the previous week, and we can get started talking about exponential and logarithm functions this week. So let's get to it. This is MAC 1140, section 4. And today is 10/26/20. Today, we're going to begin exponentials and logs. This is an important section, but it also should go fairly quickly because none of these things are entirely new to you guys. Really, the reason we cover this here is as kind of a sweep up, or to kind of collect and put things together that may have been lost or not taught especially well back in college algebra or high school algebra classes. A little note, I'll have exam 2 scores no later than Wednesday. So I had to travel out of the state over the last few days. I have not had my office with me, of course. So we'll need just a little bit more time on that, but I promise not too much. So there's only one way to get started talking about a new class of functions, and that's with a definition. An exponential function is one which can be written in the form f of x equals some constant, I'll call it c, times some other constant, I'll call it b, raised to the power x, where c is any number and b has to be positive. Some books say that the number c should be any number besides 0, but really if c is 0, that doesn't break the definition in any particular way, so I will say c can be any number. And then b has to be positive for reasons that have to do with complex numbers. If b was negative, say -1, then the value of this function at numbers like 1/2 would spit out imaginary numbers, right? Like if you have 1 to the x and you try to plug in 1/2 for x, then that would be I. If you try to plug in 3/2 for x, then that would be -I. All sorts of weird stuff happens if you don't require the base to be positive. Here, c is usually called the initial value, and b is called the base. Some books use the letter A for the base, but I like to use the letter B because it reminds us that it's the thing we call the base. The graphs of these functions all kind of look the same. There's really just 2 graph shapes. There's the exponential growth shape, which looks like this. Starts off very small over here and tends towards 0, and then gets really, really big over here. This is what the graph of c times b to the x looks like if b is bigger than 1. It has no x-intercepts, goes through the point 0, comma c, and the point 1, comma b times c, or c times b, whichever order you want to write it. This is called exponential growth. And then on the other hand, these things can also look like this, flipped over horizontally from the previous thing, still going through the point 0, comma cb. Now you have the point -1. I'll call it, it's still -1. This would be c over b. And over here you would have +1 times, and oh, sorry, 0, comma c there, 1, comma c times b here. Okay, sorry about that. Yeah, and this is called exponential decay. And this is what the graph of f of x equals c times b to the x looks like if b is between 0 and 1. So if your base is bigger than 1, you will be growing. And if your base is smaller than 1, remember it always has to be bigger than 0, but if it's smaller than 1, then you'll be decaying. All right, this function is always increasing. This function is always decreasing. I think the easiest way to start wrapping your heads around these things is to look at a few concrete examples. These abstract examples don't really help people beyond the shape. So remember, if b is bigger than 1, that's growth, and the shape is like this. If b is smaller than 1, that's decay, and the shape is like this. That's the most important thing to remember. So some specific examples. A function like f of x equals 2 to the x. Here, c is 1 and b is 2. We can make a table of values. If you plug in -1 for x, you would have 2 to the -1, that's 1/2 as the output. If you plug in 0 for x, you get 2 to the 0, that's 1. If you plug in x equals 1, then you get 2 to the 1. And we'll do one more. If you plug in x equals 2, you get 2 squared, which is 4. So the graph of this function looks like this. You've got -1, 1/2, 0, 1, 1, 2, 2, 4. Over here, if you wanted, you could plot -2, 1/4, which would look like this, -3, 1/8. And what you notice is that over here, the thing settles down on the x-axis really hard. And then as you come over this way, he grows very, very quickly. It's not a vertical asymptote. I want to be clear about that. The function isn't blowing all the way up to infinity at any finite x value. It takes its time, but it does get big really fast. If I wanted to come out one extra point here to 3, then that would be all the way up at 8, which is well off the page, right? So this is what the graph of 2 to the x looks like. And from here, it just gets steeper and steeper and steeper. There's a bunch of things that I would like to get us comfy with when it comes to these. But I don't know how much you guys remember from your previous classes. So rather than running back through everything like growth rates and growth factors, I'm going to pick a few specific topics here and kind of try to get a feel for how comfy you guys are with them. I think maybe before we do that, we should review some of the rules for exponents. Yeah, I think that's probably a wise move. I'm not a big fan of compound interest problems. So again, this is going to be a pretty brief section. As we work through this stuff, you will need to remember all of the algebra rules for exponents. For example, b to the x plus y is the same as b to the x times b to the y. B to the x all raised to the power of y is the same as b to the x times y. B to the x minus y, that's the same as b to the x over b to the y. These are the main rules. This first guy can be said that if you're multiplying like bases, you add the powers. And the third guy can be said if you're dividing like bases, you subtract the powers. The middle guy here tells us what to do if we have a power that is a product, how we can interpret that. Or if we have a power of a power, that we can interpret it as a product. So what sort of fun things can we do here? Well, let's try evaluating some more exponential functions. We've built a little table for 2 to the x and drew the graph, so that's all well and good. There are corresponding rules for logarithms. Yeah, so each rule for exponents has a corresponding rule for logarithms, and that is definitely one of the main reasons I'm reminding you of these, so I can refer back to them when we start talking about logs. Maybe a few quick notes on exponential functions, properties of exponential functions. They're always monotone. Either always increasing or always decreasing. No x-intercepts. Ever. Other important things, they're all one-to-one. So they have inverses, and that will connect to the concept of a logarithm. Other properties that we need to worry about right now? Not really. Okay, so I'll give you a second to write these things down. And then we're going to sketch a couple more graphs just by plugging in points, and we'll get a little bit of practice with our rules for exponents in doing that. Yes, yeah, the word there is monotone, M-O-N-O-T-O-N-E, monotonic or monotone. Monotone means either always increasing or always decreasing. One tone. Increasing is a tone, or decreasing, one tone, always decreasing. Okay, so for our next example, let's sketch the graph of 1/2 to the x.
Wait, Professor, I have a quick question.
What's that?
Okay, so for the rules of exponents, you said b, and then it'd be x plus y. Do you multiply just the bases, or do the exponents also multiply?
Which rule are you looking at?
The first one.
So if you have b to the x times b to the y, like 2 to the 5 times 2 to the 7,
Right.
that is the base written once raised to the power of x plus y. So 2 to the 5 times 2 to the 7 would be 2 raised to the 5 plus 7, or 2 to the 12.
Oh, okay. Okay. Perfect. Got it. Thank you.
No problem. Any other questions on these before I move on? Okay. So next we're going to sketch the graph of 1/2 to the x. And we'll do it the same way. We'll make a table. I could plug in -2, -1, 0, 1, and 2. If I want to compute 1/2 to the -2, I can treat that as 1/2 to the -1 squared, right? Using our rules for exponents. -2 is -1 times 2. So this is the same as 1/2 to the -1, which is 2 all to the 2, or 4. F of -1, that's 1/2 to the -1st power, which is 2. 1/2 to the 0, anything to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 squared is 1/2 times 1/2, that's 1/4. So the graph of this function looks like this. We'll call this -1, -2, 1, and 2. We've got -2 comma 4. -1 comma 2, 0 comma 1, 1 comma 1/2, and 2 comma 1/4. So this looks very similar to the graph that we drew a second ago, only this guy has been flipped around the y-axis. This is the graph of f of x equals 1/2 to the x. Again, you have this horizontal asymptote of y equals 0 just on one side, and on the other side it gets big. This is an example of an exponential decay rather than an exponential growth, because as we go left to right, we're getting smaller rather than larger. And that matches up with what we said about the base. Here, the base is smaller than 1, so this is exponential decay rather than growth. And the connection between this graph and the previous graph is that 1/2 to the x can be written as 2 to the -1 to the x, which using the same exponent rule is 2 to the -x. So when you compare this graph to the 2 to the x graph, and you see that they are identical, just flipped about the y-axis, you can see that as an application of our transformations work. Remember when we talked about transformations, we said f of -x is the same as f of x just flipped over the y-axis. Well, here 1/2 to the x is the same as 2 to the -x. So it should have the graph same as 2 to the x, just flipped over the y-axis. And if I flip this guy over, I get this guy. Does everybody see that? Okay. So we can have a little bit more fun with this stuff, but not a lot, if I'm honest. Yeah, let's play a little game. Maybe I'll give you the graph of an exponential function and ask if you can tell me the equation, something like that. So let's pick a nice one. How about, no, that's too easy. Still too easy. That looks good. All right, how about, yeah. So determine the formula for the exponential function. Graphed below. So all we know is that the point 2, 9 and the point 0, 1 are on the graph. We can see that this is an exponential growth function, and we know that it has to have a formula, something like c times b to the x. Can we find the numbers c and b? Who can help me out?
So C would be 1.
Good, why?
Because the y-intercept would be 0, c.
Excellent. Yeah, if we look at f of 0, that's c times b to the 0 is c times 1. And from the graph, we know that f of 0 is 1. So c times 1, which is c, has to be 1.
And then I feel like B would have to be 9.
Almost. So your intuition is good, but this isn't 1 comma something, it's 2 comma something. So can we be a little bit more careful and use this type reasoning to figure out b from this second point?
Right.
Let's
Because
go ahead and update our f of x. We know c is 1, so f of x is just 1 times b to the x. Now, this point tells me f of 2 is 9, right? But also f of 2 has to be b to the 2. And from the graph,
yeah, it would be 3.
yeah, good. F of 2 is 9. So we get the equation b squared equals 9, which means b has to be 1 of plus or minus 3. But of course, b can't be negative. we're never allowed to have a negative base in an exponential function. So like Ron and Lily said, b has to be 3. Because we don't allow for negative bases. Even in complex analysis, we try to avoid those. Okay, so then we learned that b is 3. So f of x, my function here, is 1 times 3 to the x, or just 3 to the x. I want to emphasize how quickly these functions grow, right? They're called exponential because the variable is in the exponent rather than in the base. With the polynomial functions and power functions that we've played with so far, you had your variable raised to some constant power. So the variable was in the base and the power was constant. Now the base is constant and the variable is in the power. This is a much faster growing function than like x cubed. 3 to the x and x cubed are very different functions. 3 to the x is an exponential. X cubed, or x to the 3, that's a polynomial function. And the polynomial x cubed grows way slower than the exponential 3 to the x. This might be best illustrated in Desmos. You don't have to write this down. I just want you to look at this with me and try to remember the basics here. I'm going to graph the function we just graphed. 3 to the x, and compare that to x cubed. So the blue is x cubed and the red is 3 to the x. It might look like they're pretty close, but as you go further and further out here, the red way overtakes the blue. Let me scale my y-axis for this. Make this a little more appropriate. So let's scale this up to like 5,000. And you see right away the red overtaking the blue. The red grows so much faster. Like right here, when x is equal to 6.97-ish, the red is all the way up at 2,000. But at that same x value, the blue, that's 7-ish, is 343. I'm just comparing these 2 points. All right, at the same x value, at x equals 7, the red function, which is the exponential, is much, much larger than the blue function, which is polynomial. So the exponential grows way faster. Even though that polynomial, that blue function, grows pretty fast, it's destroyed by the red function. And this is true in general. Exponential functions outgrow polynomial functions across the board. But the shapes are not super interesting. You know, from a graphing perspective, they all kind of look like this. If the base is bigger than 1, they have this shape. If the base is smaller than 1, they have the decaying shape. So what I'd like to practice now is applying some of what we learned about transformations to exponential functions. Can we sketch the graph of f of x equals 3 plus 2 raised to the 1 minus x power? So to do this, I need to start with a parent function. Identify some transformations that we can apply to that parent function to get this function, and then graph the transformed function. So you have a new family of parent functions, these basic exponentials. like 2 to the x. And then we have to figure out how to see f as a transformed version of that. That may be helpful to rewrite f of x as 2 to the negative x minus 1 plus 3, like this. In the same way that factoring negatives and rewriting the order of addition was helpful back when we were learning how to graph transformations at first. So what sort of transformations do you see that will take you from 2 to the x to this guy? Good.
Move up by 3 units.
There's definitely a shift up by 3 units. Those are all correct. Everybody who said that is correct. What about this shit here? What does this stuff tell me? Flipped how? Vertically or horizontally? Flipped. So it'll be flipped about the vertical axis, but that's a horizontal flip. So the language here maybe could be confusing. Remember, 2 to the negative x, this is horizontally flipped from 2 to the x. So I don't want to clutter things. The transformations here there is a horizontal reflection. That's coming from this negative, right? When you multiply on the inside by a negative, things flip over horizontally. There is a horizontal shift. That's coming from this -1. It's a shift to the right by 1 unit. And then there is the vertical shift. This one is up 3 units. So I take the graph of 2 to the x and I apply these transformations in this order. Here's 2 to the x. It's got 0, 1, 1, 2, and we could say -1, 1/2 if we wanted. Let's do that. So this is my y equals 2 to the x graph. I want to reflect horizontally. That will give me something looking like this. This one I'll have -1, 2, 0, 1, and +1, 1/2. That's just doing the horizontal reflection. Yes, the shift right is coming from the -1 inside there. So this is the graph of y equals 2 to the negative x. And now we do the shift to the right by 1 unit. So 1, 1/2 is going to go to 2, 1/2. So I'm dragging this point to the right 1 unit. 0, 1 is going to go to 1, 1. -1, 2 is going to go to 0, 2. And the overall graph here, now look like this. This is the graph y equals 2 raised to the negative x minus 1. And now we do the vertical shift up, and that will get us to our final graph. So I'll draw this one a little bigger. I bump everything up by 3 units. So I'll draw in my y equals 3 line. Two comma 1/2 goes to 2 comma 3.5. I'll mark this as 1, 2. Because I'm bumping this up by 3 units. 1 comma 1 is now 1 comma 4. And 0 comma 2 is now 0 comma 5. And the overall graph should go up a little bit more steeply. Looks like this. So this would be our final transformed graph. Notice that the horizontal asymptote moved up along with everything else when we did our vertical shift. So we got to follow the points that we moved. So why a 1/2 here? Is that what we're asking? Why is this point 2 comma 1/2? Because I started here on the graph of 2 to the x, which has the point -1 comma 1/2. Because when you plug x equals -1 in here, you get 2 to the -1, which is 1/2. When I reflect this graph horizontally, the -1 comma 1/2 moves over here to 2 comma 1/2. And then when I drag that to the right by 1 unit, that goes to 2 comma 1/2. Finally, when I bump 2 comma 1/2 up by 3 units, that means I'm adding 3 to that y value. That becomes 2 comma 3.5. Or you could write that as whatever it is, 7/2 if you like it as a fraction. All right, cool. Other questions on how we got this transformed graph? Yes, if you can factor a negative inside, you should do that. So 1 minus x, it's hard for me to tell what's going on there. The x is negative, which makes me think horizontal reflection. And then there's a 1 doing something on the inside, but it's not obvious whether the horizontal shift is going to be left or right. If you factor the negative, it gets easier to see, because then you have an x minus 1 on the all the way inside, which tells you shift to the right by 1, and your whole interior is negated, which tells you have a horizontal reflection. So factoring the negative inside, just like when we did the transformations of the square root functions, you remember those, or you may want to go back and look at those, is a useful trick. So a fair amount of your homework is going to be this. I'll give you a function and I'll ask you to match the graph, or I'll give you a graph and I'll ask you to come up with the function. It's not too hard. Yeah, so when you have both a horizontal reflection and a horizontal shift, it's important that you factor the negative in order to be able to see which way to go. Yeah, I agree that it's confusing otherwise. Exponential functions are interesting for a lot of reasons. One of which is this thing called compound interest. Compound interest is what happens when you take a simple interest scheme, like you're going to pay me 5% per day, and I keep checking in over and over again to ask, how much do you owe right now? When I do this in college algebra classes, I like to go through the whole procedure of cooking up the compound interest formula. I'll try to explain it quickly. So suppose you loan me $10 at interest rate of 2% per month, say. Well, then after 1 month, I owe that $10 plus 2% of $10. Right? I think we would all agree that. I owe you the money that you lent me plus the interest for the amount of time that has passed. And if you're charging me 2% per month, then I would at that moment owe you $10 plus 2% of $10. This is 10 plus, what is 2% of 10? What's 2% of 100? I'm sorry? So 2% of 100 would be 2, right? So 2% of 10 is 0.2. So I owe you $10.20 after 1 month. After 2 months, I owe, well, let's see, I owed you 10.2, right, or $10.20 from last month, plus the new interest from this month, which is 2% of 10.2. And we would continue in this way. So what would we have here? We can do the computation, 2% of 10.2. Another way to write this is 10.2 plus 0.02 times 10.2. And you can factor out the 10.2. And here you'd have 1 plus 0.02. If you continue this process, then after n months, I would owe 10, what's the right way to say this? I would owe you the $10 times 1 plus 0.02 raised to the n. So the simplest way to think about this is you have your principal times some number raised to the amount of time it's been. So after n months, I would owe you this much. Each month, we're slapping on another factor of 1 plus 0.02. And these pieces are coming from where they appear to be coming from. Compound interest is what happens when I want to check in on this process all the time. So rather than checking in once per month, I want to check in every day, every hour, every second. So rather than owing you the full 2% of that $10, if I check in just a day later, I wouldn't owe you the full month's worth of interest. I would just owe you the amount of interest for the time that has passed so far. So in the same situation, suppose we do the same thing. You loan me $10 at a rate of 2% per month. But I want to know after 1 day how much I owe. Well, definitely I owe you that $10. And I owe you some amount of interest. But it hasn't been a whole month yet. So I don't owe you the full 2% yet. It's only been 1/30th of 1 month. So I owe you 2% of $10 over 30. Are you following this? This is a little bit wonky, but I promise you, if you think about it like this, it will work just fine. You loaned me $10. So I owe you that $10 back. You said you were going to charge me 2% interest per month, but it hasn't been a whole month yet. It's only been 1 day. So I owe you the $10 you loaned me, plus whatever interest has accrued so far. Since it's only been 1/30th of a month, rather than owing you the full month's interest, which would be 2% of $10, I owe you that divided by 30. Now, if you write this out, this is 10 plus 0.02, that's the 2%, times 10 over 30. Factor out the 10, and you get 10 times 1 plus 0.02 over 30. And those of you who have worked with the compound interest formula before are probably starting to recognize the pieces. Here's your principal, here's your rate, here's the number of compoundings per unit time. What about after 2 days? Well, I would owe you all of this from the previous day, right? And then I would owe you whatever interest has accrued on that in the 1 day that's gone past. There it is, we're getting to it, I promise. So this is how much I owed after 1 day. To figure out how much I owe after 2 days, I take the amount I owed after 1 day, and I add to that whatever interest has accrued since then. That would be this amount, because this is what's accruing interest, times whatever, what's the right way to say this? Times the factor that determines how much interest has picked up in that second day. Now that second day is again just, what's the right way to say this? So here's what I owed you from the previous day, and then I take that amount and I slap on another 2%, 1/30th of 2% of that. And if you factor everything out here, what you'll get this would be squared. Yeah, we factor out the 10, we'll have those. And the general result here for compound interest is if you loan me P dollars, or P whatever, lira, yen, at rate R% per unit time, then after t units of time, I'm just saying R units time, compounding, we should say. So each time we check in, like here I was compounding once per day, I was checking in once per day to see how much I owed, compounding n times per unit time. Then after t units of time, I will owe P times 1 plus the interest rate divided by the number of times you're compounding per unit time, like the 30 here, all raised to the t times n. And usually we call this function a of t. So P is the principal. It's the amount that you lend me at first. R is the amount of interest you're charging per increase in T. So usually time is measured in years. We could say we're charging 2% per year or 5% per year. Often they leave off the per in these problems. It's very frustrating. They should not do that. But if it's not stated otherwise, you can assume that the units of time are years. And then compounding n times, in other words, how often are you checking in to see how much I owe you? N times per unit time. So P is called the principal. R is called the nominal rate, or sometimes just the interest rate. And N is the number of compoundings per unit time. These problems where I tell you an interest scheme and ask you how much I owe after 10 years or 5 years bore the shit out of me. They're not interesting problems. But there is one interesting thing that comes from studying this, and it's the number E. So I'll probably include one problem where you need to do a computation like this. So I'll do one example for you here. Suppose you borrow $8,000 at 1.5% per year. And this is compounded daily. Find the function a of t and determine how much you owe after 5 years. All right, so you get this loan for $8,000. You know that the interest rate is 1.5%, and that's yearly. You know that they're compounding the interest every day. Can we figure out how much you'll owe in general after t years? Can we find the formula for a of t? And then can we figure out how much you owe after 5 years? So we know that this function a of t is always the principal times 1 plus the nominal rate over the number of compoundings raised to the number of compoundings times time. So the variable here is t. Everything else is constant. The principal was $8,000. 1 is 1. R, your interest rate here, is 1.5%. As a decimal, 1.5% is 0.015. Percent means out of 100, so you just divide this by 100. N, the number of compoundings per unit time Here we're compounding daily and we're measuring time in years. So n is 365. So this would be your function. And we can do a little bit of calculation. Let's figure out what that base in there is. So we can rewrite this more nicely. One plus 0.015 divided by 365. This is 8,000 times. I'm going to come back here and do a bit of algebra for you. So this is where those rules for exponents are going to come in again. I have this whole base, 1 plus 0.015 over 365, raised to the 365 times t. Since those powers are being multiplied, I can rewrite this like this. Is everybody following from this line to this line? Oh. So what we're using there is this rule for exponents. Where did that go? Is that back down here? I seem to have misplaced it. It's the third or second rule for exponents. That b to the x all to the y is the same as b to the x times y, to go from here to here. I'm thinking of this thing as b, this number as x, and this number as y. So this is the same as b to the x all to the y. And now we can compute this number raised to the 365, and that will be the base. So this is like 1.01511. I'll write the whole thing they gave me here. All to the t. So is this an exponential growth function? Yeah, because the base is bigger than 1. And that matches up with our intuition that this function should be growing because the amount that I owe or that you owe should be going up over time. And if you remember some of the lingo from college algebra, you can talk about the growth factor and the growth rate. You can talk about the nominal interest rate versus the effective interest rate. But for us, we just wanted to find this function, express it as nicely as possible. That's what we've done here. Although stopping here would be acceptable. And then the last thing we wanted to do is answer the question, well, how much do I owe after 5 years? That would be A of 5, which is 8,000 times this number to the 5th power. And we can compute that. Nope, does not want to play. No. All right, we'll take this number, we'll copy it. Raise that to the 5, then multiply that by 8,000. And we get the answer here, which is 8623 times 0.0599. So these compound interest things are a little bit boring. You should be comfortable going through this procedure. That's important. Making sure that you can get to this, that you understand the algebra steps necessary to get to this step, that's a sort of big deal. We're really just using this rule. So we simplified this to this by taking this power, which was multiplied outside, and bringing it inside. Then the step from here down to here, that's a matter of taste. It doesn't really help us, but it does allow us to see what the base of the function is more intuitively. I can see that the base here is just a little bit bigger than 1, which tells me that this is a slow but growing exponential. And then of course, being able to plug in 5, it's something I'm sure everybody could do. It's not challenging. So the only kind of tricky stuff here is this bit of algebra that gets you down to here. Are there any questions on the algebra steps we used in the blue box right
I have a question.
Yeah, please.
What happens if I multiply 365 times 5 before all those steps? Will I get it wrong?
If you follow the order of operations, okay. So you could calculate a of 5 from this line. You could take 365, multiply that by 5, set that number aside, then compute this number, then raise that number to the result from 365 times 5, and then multiply by 8,000. But you do need to be very careful with your order of operations. If you just type it into a calculator without being very careful with your parentheses, if you type this in left to right, it will not give you the right answer. It will take this, raise it to the 365, then multiply that by 8,000, then multiply that by t. So one of the reasons we like to put it into this form is now you've got your standard exponential form, which means you can type it into a calculator like this and you'll get the result correctly. But more important than that is being able to see the size of the base to understand how quickly the function is growing. So being able to get to this step is important. It's not something that you should skip over. And it is something that I would be within my right to test on. Like take this compound interest scenario and put it into the formula c times a to the x, which is what we have here. So while it's possible to do this without going through those algebra steps, you must become comfortable going through those algebra steps. Is that you feel okay with that answer?
Yes, thank you.
Cool, of course. Any other questions on what we did here or why? Okay. So we have a few minutes left. And in those few minutes, what I'd like to talk about is why compound interest shows up here at all. I mean, sure, math teachers like giving you stuff that's useful in the real world when we can. But the real reason we care about this is because there's a man named Leonhard Euler. And that last name, I know it looks like Euler, but it's really Euler. It's German, Swiss German. And he studied the compound interest formula as a function not of the variable t, but of the parameter n. So Euler said, forget r, t, and p, what happens as n goes to infinity? So you're looking at 1 plus 1 over n to the n. All right, when we say forget r, t, and p, I don't care about the rate, I don't care about the principal, and I don't care about the time. Yeah, I think that's the correct spelling. Apologies if it isn't, but yeah, Leonard, Leonard. It's a weird spelling of Leonard. So he ignored those three variables, r, t, and p. He just wants to study this as n gets bigger and bigger and bigger. If you have your phone number here, you can do something fun. You can plug your phone number in for n. One of the professors at Santa Fe, Vince Locascio, likes to have people do this. I'm not trying to give out my phone number right now, so let's grab Santa Fe's phone number. Here we go. 352-395-5000. We're interested in what happens to this expression as n gets very, very large. The 1 over n piece in here is going to try to get really small. 1 divided by a big number, that's a very small number. But then we're adding 1 to that, so it's going to be a little bit bigger than 1 on the inside. And then we're raising that whole thing to an enormous number. I can guess the first few digits of this. This will be 2.718, maybe a 28 after that. Because the limit of this apparatus oh, did I draw something wrong? 352. 352, 3955, yeah. You see, 2.71828 blah, 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 blah. As n gets bigger and bigger, this number 1 plus 1 over n to the n gets closer and closer to a number that in honor of Leonhard Euler we call E. And that number has the first few digits 2.71828, blah, 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 blah. It's an irrational number like pi, or the square root of 2. It's a transcendental number, which pi is, but the square root of 2 is not. This means that you can't write it as a ratio of whole numbers. There's no nice fraction form for E. And it's also not the solution to any polynomial equation with whole number coefficients. It's a very special number. And it's so special, it shows up in so many different places that we call this two names, either Euler's number, again in honor of the man, or the natural base. Because the function e to the x the exponential function formed with e as its base has a lot of nice properties. So I'm going to leave it here for today. And starting on Wednesday, we're going to talk about the natural exponential, which isn't really special from other exponential functions, aside from some very nice calculus properties. And then we're going to talk about the inverse to these exponentials, which are called logarithms. Now, I posted something for you guys last week after your test. And one of these, this first item, if you didn't go through this, that's not the end of the world. I'm hoping or trusting that most of you remember the basics about exponential functions from your previous algebra classes. However, this second thing, I want everybody to print this and work through it. It's an excellent resource, and it will save your butts when it comes to logarithms in every sense except for the graphs. So next time we're going to introduce the logarithm function as the inverse to exponential functions. We will talk about all of the properties that are in this worksheet. If you did not go through this worksheet last week, please go through it as soon as you can. All right, go through it today, tomorrow. Don't wait until after class on Wednesday, because if you haven't gone through this, class on Wednesday will feel challenging. If you're stuck on any of this, you can come by my office hours. I have my normal office hour today and also a normal office hour tomorrow. And I'll be happy to work with you on some of these things. It's totally fine if you get stuck in here. I just want you to get in and work with it a little bit so that the notation and the concepts aren't completely foreign. And that's where we'll pick it up next time, is with logarithms and graphs of logarithms. Yeah, homework will be up a little bit later today. Yep. Any other questions for me before we get going? Okay, then I will see you guys on Wednesday or in office hours if you come by. Hope you all have a lovely rest of your afternoon, and please do get started on that homework. It'll be up in just a few minutes. Take care.